Okay, welcome back. We said there were three types of reactions we were going to talk about. We said they weren't the only three types of reactions, but there were three pretty important ones, and they cover quite a few reactions that you would possibly run into out there. And we talked about precipitation reactions in the last video. Well, what we're going to do now is we're going to talk a little bit about acid-base reactions. So let's talk about those real quick. So I guess if you're going to talk about acid-base reactions, I guess the first thing you really need to talk about is, what exactly is an acid and what exactly is a base. Well, acids, there's three different definitions actually for an acid. I'm going to give you one today, and then I'm actually going to change it on you later on down the road. And I could change it again, but I'm not going to do that. I'll only change it once, somewhere down the road. But for now, a good working definition of an acid: acids form H plus in a water solution. So, and sometimes you'll see H3O plus, because actually that H plus is very reactive and it globs onto a water molecule. You end up with H3O plus, something called a hydronium ion. But for our intents and purposes here, we'll talk about H plus forming in the water. Okay? If you have something that gives off H plus, it's an acid. That's the Arrhenius definition of an acid. Right? There are two types of acids you run into out there. There are what we call strong acids, and there's what we call weak acids. All right. Now, when we talk about strong and weak acids, we're not talking about concentration. I could have a very dilute solution of a strong acid, and I could have a very concentrated solution of a weak acid. Strong versus weak means something fundamentally different. So let's talk about your strong acids first. So what makes a strong acid a strong acid? Well, strong acids completely dissociate in water. When you put them in water, they break apart completely. Right, and that's what makes them strong. There are 6 common strong acids that you need to know on sight. And I told you in the last chapter, you might as well memorize them now because you're going to need to eventually. Well, here we are. Okay, you need to know these 6 on sight. 3 of them are hydrogen with a single atom. 3 of them are hydrogen with a polyatomic ion. The 3 with a single atom are your 3 halogens there, your chloride, your bromide, and your iodide. See, they're all sitting there in the periodic table in that column. HCl, HBr, HI. That's hydrochloric acid, hydrobromic acid, hydroiodic acid. The 3 with a polyatomic ion are hydrogen with a nitrate, hydrogen with a sulfate, hydrogen with a perchlorate. 3 polyatomic ions you're supposed to know and memorize. All right. So with the nitrate, that is HNO3, that's nitric acid. HClO4 is perchloric acid. That's the one everybody always forgets. The only one that works slightly different would be H2SO4, which is called sulfuric acid. It's H2 because remember a sulfate has a -2 charge, so you got to know your polyatomic ions. So therefore you need 2 little H pluses to make that neutral. So it's H2SO4. All right. So you actually get twice as much H plus for your money with sulfuric acid there. But it's still a strong acid because it breaks up 100%, just like the other 5. When you see those 6, you need to recognize those on sight as acids, and you need to recognize them as strong acids. All right, so what makes them strong? Well, when I put HCl in water, what it does is it breaks apart to give me H plus and Cl minus. All right, what makes HCl an acid? Well, the fact that it's giving off this H plus in a water solution. What makes it a strong acid? Well, the fact that when my HCl goes into the water, it completely breaks apart into H plus and Cl minus. 100% dissociation for weak to moderate concentrations. That's the standard disclaimer there. But that's what you're going to be dealing with, so don't worry about it. The key is if you were able to look inside a beaker of hydrochloric acid, what would you see? Well, you'd see a whole lot of water molecules because it's mixed up in water. But you'd see some H plus, technically, as I said, H3O plus floating around. You'd see some Cl minus floating around. But what you would not see is you would see no HCl molecules floating around in solution. 100% dissociation. Everything breaks apart. And that's what makes it a strong acid. Make sense? Okay. Well, if it's not a strong acid, I guess it must be a weak acid. So what makes a weak acid a weak acid? Well, weak acids only partially dissociate in water. Okay, So there are a couple of thousand different weak acids out there. Do you have to memorize all the possible weak acids that you run into? No, you don't. Okay? Here's the way it works. If it's not one of those 6 strong acids up here, it must be a weak acid. And that's how I would know them. Now you can go, if you want to, you can go the other way around. You can memorize 3,000 different weak acids, and if it's not one of those, it must be a strong acid. I think I would probably memorize the 6 and then go that way. That seems to me to be the easiest way to go. All right. Well, you'll notice that we didn't talk about fluorine. We talked about chlorine, bromine, and iodine there, but we didn't talk about fluoride up there when we talked about the strong acids. And that's because HF, that's hydrofluoric acid, is actually a weak acid. So when I put hydrogen fluoride here, HF, in water, it breaks apart to give me H plus and F minus. So what makes HF an acid? Well, the fact that it's giving off H plus here in a water solution. So what makes HF a weak acid? Well, you see this double arrow here? This double arrow means something. For now, what I want you to do is I just want you to think of it as it means partial. In other words, not complete. All right? It actually means something else. And we'll talk about it when we get a little bit further on down the road. All right? But partial. So what that means is if I were able to look inside a beaker of hydrofluoric acid, what would I see? Well, I'd see a lot of water molecules because it's mixed up in water. I'd see some H plus and some F minus floating around. Right? But I would also see some undissociated HF floating around in there as well. So less than 100% of dissociation. I would see some of this, and some of that all in the same beaker. And that's what makes it a weak acid. If it only breaks up 99%, it's still a weak acid. If it breaks up 1%, it's still a weak acid. All weak means is breaks up less than 100%. All right? Now, generally speaking, most weak acids break up much less than 100%. They don't even break up 50%. Most weak acids actually break up less than 10%. HF breaks up probably around 7 to 8% dissociation generally. So basically that means 92% of the HF molecules actually stay together and only 7 to 8% of them actually split apart. But some do break up and they form H plus, and that's what makes it an acid. The fact that it breaks up less than 100% is what makes it a weak acid. HCl completely breaks apart, that's what makes it a strong acid. Make sense? HCl is probably the most common strong acid you run into. You're carrying some with you right now. That's actually your stomach acid. Stomach acid is primarily hydrochloric acid, actually. So yeah, you've actually got some with you there. Probably the most other common one you run into would be sulfuric acid, H2SO4. That's battery acid. So, you know, like a car battery is full of acid, battery acid. It's concentrated, very concentrated sulfuric acid. That's why you don't want to get that stuff on you. You'll hold through you and you hold through your clothes and things like that. If you have an acid that is stronger than 100% H2SO4, it is actually classified as a superacid. And boy, that's a whole nother lecture. Maybe chemistry club someday we'll talk about superacids and what makes them so super. But yeah, that's actually the break point right there is the sulfuric acid. Okay? All organic acids are weak acids. If you see a COOH on the end of something, it's an organic acid and they're all weak acids. Things like acetic acid, for example. Where do you find acetic acid? Well, you find that in vinegar. Vinegar is about 5% acetic acid. So take the smell of vinegar, multiply that by 20. That's what pure glacial acetic acid smells like. We keep it in the fume hood if we can. All right, but yeah, if it's an organic acid, ascorbic acid, vitamin C, citric acid comes from citrus fruits. Those are all weak acids. Okay. And so, yeah, because they only partially break up in water. All right? Okay. Well, if it's not an acid, I guess it's a what? Well, I guess it's a base. See, these notes, they just write themselves after a while. I just stick it on autopilot here. All right? So what makes a base a base? Well, bases form OH minus in a water solution. All right, and again, we'll change that definition someday, but for now, that'll work. All right. Turns out there are two types of bases. Can you guess what they might be? Well, yes, they would be strong bases and weak bases. So what exactly is a strong base anyway? Get that over there. Well, strong bases completely dissociate in water. All right. Your strong bases are your group 1 and heavier group 2. And when I say heavier group 2, I mean calcium on down hydroxides. You need to know those on site. All right. If you've got to have them written out, that would be lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, and then group 2 with calcium on down. So calcium hydroxide, strontium hydroxide, and barium hydroxide. All right. Notice these are also your soluble hydroxides. See? And so that's probably the reason why there's such an overlap there. You know, if it's not soluble, then it won't go into solution, so it won't dissociate at all. So you can't have complete dissociation. But these are my soluble hydroxides, and so that's probably why these are your strong bases. So if you got a periodic table, all you got to do is look and see if the cation's in group 1 or calcium on down. And of course, you'll always have a periodic table with you on the test. All right. The only difference between your group 1 and your group 2 is how much hydroxide you get. So let's say, for example, calcium hydroxide. What happens when I put that in water? Well, it breaks apart to give me Ca2+, and I get 2 hydroxides out of the deal. Okay, so I get twice as much hydroxide for my money here with calcium hydroxide as I do with sodium hydroxide. But they're both still strong bases, because it doesn't matter how many hydroxides I get. The key here is, if I looked inside a beaker of calcium hydroxide, what would I see? Well, I would see some calcium 2+ floating around, some hydroxide floating around, but what I would not see is any CaOH2 molecules floating around. Okay, 100% dissociation. Everything breaks apart, and that's what makes it a strong base. You might get twice as much hydroxide out of this as you would, say, lithium hydroxide, but lithium hydroxide completely breaks apart, 100% dissociation, and that's what makes them both strong bases. It's not a question of concentration, it's a question of how much does it dissociate. Now, obviously, if it dissociates more, you're going to have a higher concentration of hydroxide if you have the same concentration of your base. So strong bases will give you more OH minus than weak bases would at the same concentration. But it's not strictly about concentration, it's about how much does it break apart. That's the key. All right, probably the most common strong base that you've run into would probably be this one right here, sodium hydroxide. Sodium hydroxide is otherwise known as lye. You see this used to make soap, lye soap. Probably heard of that before. But yeah, basically you take a fat of some sort, or an oil. An oil is basically a fat that is liquid at room temperature. We're not talking about petroleum here. We're talking about just regular, oils and things like that, peanut oil and things like that. And you render it with sodium hydroxide, and it breaks that fat down into sodium salts of long-chain carboxylic acids. And that's actually a soap. And so that's actually how they make soap. Sodium hydroxide is used for that quite a bit. Sodium hydroxide is also used in things like liquid plumber, Drano, if you have a clog in your sink. Here's the thing about bases. Acids get all the press. Acids, you don't want to pour any acid on you because it'll eat right through you, right? Well, bases actually will do the same at high concentration. And in fact, bases are really good at dissolving proteins, denaturing proteins. What is your skin made of? Yes, it's made of protein. So actually, base burns tend to be more extensive, they tend to be deeper, they tend to take longer to heal. I'd much rather be splashed with an acid than a base, same concentration, same strength, because the base burn actually probably will be worse. Even though people always talk about acids, they don't talk about bases so much. Well, if you got a clog in your drain, you probably got hair or something down there, probably something organic. And so basically you pour that liquid plumber down there, which is really just sodium hydroxide, maybe potassium hydroxide, a little bit of that in there, I don't know. But it's just basically, no pun intended, a base. and it'll just eat through the clog. And that eats through the clog, your water starts flowing again. Could I pour a strong acid down there and eat through the clog? Probably. But what do acids react with besides the clog? Well, they react with metals. And so not only will it eat through the clog, it'll eat through your pots, which tends to kind of defeat the purpose there. And so, yeah, that's sodium hydroxide. Yeah, you can make it into a gel or something like that, so it's higher density and it kind of sinks down to where the clog actually is, so it's more concentrated. But and that's really what it is. It's just basically sodium hydroxide. Okay, so that's probably the most common one I think you probably run into. Okay, 100% dissociation, that's what the single arrow means. Okay, if it's a base and it's not a strong base, what would it be? Well, it would be a weak base. All right, so again, there's thousands of weak bases out there. And if you want to, you can memorize all the possible weak bases. All right, but your strong bases are your group 1 and your group 2 hydroxides. If it's not a strong base, I guess it's a weak base. That would be the easiest way to go. So see, if you don't know your strong acids and you don't know your strong bases, you won't know your weak acids and you won't know your weak bases. Memorize your strong acids, memorize your strong bases. All right? Probably the most common weak base, all organic bases are weak bases, by the way, but probably the most common weak base that I think you probably have run into would be ammonia. Okay, and that would be NH3. What do we use ammonia for? Well, lots of things. Cleaning supplies, Windex, things like that. Glass cleaner is probably the most common, but I mean, there's a whole lot of other things you can use ammonia for, probably actually more useful than that. Fertilizer, it's used as a precursor for fertilizer. In fact, sometimes they just use anhydrous ammonia as a fertilizer, but usually ammonium nitrate. But you got to make that from ammonia. It's a precursor to a lot of explosives. There's all sorts of things you can use ammonia for industrially. Precursor to feedstock for cattle. Very versatile, very useful chemical that you can use for a lot of things, both good and evil. Chemicals are morally neutral, by the way. They're not good or evil. It's what you do to use them, as to what makes them good or evil. So, sometimes we assume that when you walk in the door, you have a fully formed set of ethics. Just because you're very intelligent does not necessarily make you a good person, and vice versa. They don't necessarily go hand in hand. And sometimes as a chemist, what happens, or as a scientist, you run into a problem and you think, boy, this is a really interesting problem. I need to solve this problem somehow. And you get so wrapped up in the problem, you don't think about, okay, well, once I solve this problem, what am I going to do with it? And so, a lot of the people that worked on the atomic bomb back in the 40s, extremely interesting project, and very interesting physics and chemistry there. And when they actually dropped it, a lot of them were just horrified because, again, it comes down to the big number thing. Numbers in scientific notation are just numbers, and you don't actually understand what they really mean until they drop that bomb. And a lot of people were kind of sorry they worked on it at that point. We could get into a debate, whether it was a right thing or the wrong thing to do, but this isn't your government class. This is a chemistry class. But that being said, generally speaking, it's important to be intelligent and be a good scientist. It's also important to be an ethical human being. And just because you're working on one doesn't necessarily mean you're working on the other. Try to use your powers for good if you can. Don't use them for evil. All right? Okay. Well, anyway, get off the soapbox here. So ammonia, NH3, is actually a base. A base? Well, see, OH minus, what makes it a base? Well, here's the way all of your weak bases work. When you write the equation for the dissociation of a weak base, you write the molecule, and then you're just going to add water. Always, just add water. There's a lone pair of electrons sitting on this nitrogen up here. Okay? And why that is, we'll talk about it later, but just there is for now. So when you write the equation for the dissociation of a weak base, you're going to write the molecule down, and then you're going to add water. Just add water. All right? So this nitrogen looks at this oxygen and says, I see you've got 2 extra H's here. I think I want one of those. All right? And the oxygen says, nope, don't think so. And so what I've got is I've got kind of an H plus tug of war going on here for that hydrogen. Now the nitrogen already has a pair of electrons here, so it doesn't need the electron that normally comes with the hydrogen. It just needs the H. So what we're going to do is we're going to add an H plus to this NH3. Now if you want to think of it in terms of adding an H plus, you can. If you want to think of it in terms of adding an H and then adding a plus, you'll get the exact same answer. So either way will get you where you want to go. So let's say, for example, the nitrogen wins the little H plus tug of war and pulls an H off of this H2O. All right? Well, if you add an H to NH3, what do I get? Well, I get NH4, right? If it was neutral and I added a plus to it, what charge does this thing have now? Well, now it's got a +1 charge. And so I get NH4 plus, which is your ammonium cation, which is one of your polyatomic ions you're supposed to know. All right? So what does that leave the water with here? Well, now my oxygen has 1 less hydrogen, and I'm going to take away a plus charge from it. If it was neutral and I take away a plus charge, what charge does it have now? Well, it's got a minus charge, and so therefore I end up with OH minus. So what makes ammonia a base? Well, the fact that I'm forming OH minus here in a water solution. Does the OH minus come from the ammonia? No. It comes from the water that's reacting with the ammonia. But do I still end up with OH minus in a water solution? I do. And that's what makes it a base. What makes it a weak base? Well, if I were able to look inside a beaker of ammonia, I would see some NH4 plus and some OH minus, but I would also see some undissociated NH3 molecules, because the NH3 doesn't win the tug of war all the time. So I'd see some of this, I'd see some of this, and some of this, less than 100% dissociation. And that's what makes it a weak base. Now, we talked about how weak acids will break up less than 100% and generally less than 10% generally. Weak bases pretty much work the same way. Weak bases generally will break up less than 10%. Ammonia for most solutions usually less than 5% or so, something like that. So 95-96% of ammonia molecules just are ammonia molecules floating around, and only 5 to 6% of the time do they win the tug of war, and you end up with that. But you do end up with some OH minus. That's what makes it a base. The fact that it breaks up less than 100% is what makes it a weak base. And that's what strong and weak mean here. They don't mean concentrated versus dilute. They mean, does it break up 100%? Does it break up less than 100%? All weak bases pretty much work the same way. So this is acetate, one of your polyatomic ions you're supposed to know. All right, how would I write the equation for that? Dissociation. Well, I'd add water. I'd pull an H plus off the water, and I would add it to my CH3COO minus. So I end up with CH3COOH, add a plus to it. It went from -1 to neutral, so there's acetic acid right there that you get. And I pulled an H plus off the H2O, and end up with water. Off the water, I end up with OH minus. This is what makes acetate a base. The fact that it doesn't always win the tug of war, this little double arrow here, is what makes it a weak base. All right? But notice it's the same pattern. Molecule or anion plus water, add the H plus to the molecule or anion, you end up with OH minus, which is what makes it a base. And that's how you write the equation for the dissociation of a weak base. The OH minus doesn't come from the molecule itself, it comes from its reaction with water. But you still end up with OH minus, which is what makes it a base. Ammonia is probably the most common weak base that you probably have run into. Fluoride is a weak base, actually. You can write the equation of dissociation of that if you want to. You see that in like water supplies, at about 1 part per million. Toothpaste, things like that. That's another common weak base, I guess, probably you've run into out there. Okay? If I gave you an acid or a base, could you classify it as either strong or weak? You can if you know your strong acids and your weak acids, because the weak bases and weak acids are everything else, basically. Okay. Well, now that we know something about acids and bases, let's play with them. Let's start mixing them together here. Okay. So acid-base reactions. All right. Now, there are thousands of weak acids and strong acids out there, and thousands of bases. Is there any way you're going to be able to memorize what I'm going to throw on the test at you? No, there's no way. But here's the nifty thing. There's only 4 types of acid-base reactions that you would run into. And in reality, you only have to memorize 3. So if you know what type of reaction it is, then you can write the equation for that particular acid-base reaction without memorizing everything. You just got to be able to recognize 3 patterns. That's a whole lot easier. When you're doing this, you can go through the total ionic equation and then start canceling stuff all over the place if you want to get the net ionic. But pretty much what they're going to ask you for is they're going to ask you for the net ionic equation for this stuff. So here is a nice little shortcut for you when you're doing these reactions. What we're going to do is we're just going to write down what we call the reacting species. The reacting species is the species that actually reacts in your net ionic equation. Well, we call it the reacting species. See, it's not that hard, is it? If you see a strong acid, the reacting species is H+. So if you see any strong acid, write down H+. If you see a strong base, the reacting species for a strong base is OH-. So if you see a strong base, write down OH-. It's that simple. All right. If you see a weak acid or a weak base, the reacting species is the molecule itself. All right. Do you remember how we talked about how weak acids and weak bases break up less than 50%? In fact, they usually break up less than 10%. Well, if that's mostly what's floating around in the solution, that's probably going to be what's mostly going to react. And so the reacting species is the molecule itself. Okay? So how do I apply this? Well, let's say, for example, I gave you a strong acid, strong base reaction. All right, so name me a strong acid. Well, how about HCl? That's what I'm hearing out there. How about a strong base? Well, 85% of the time, people actually give me sodium hydroxide. Always. That's probably what you're thinking out there, wasn't it? Okay. But we're going to do something different here. I'm going to throw you a curve. Let's look at calcium hydroxide. That's a group 2 hydroxide, and I know that's a strong base. But it doesn't matter. If you did sodium hydroxide, it'd actually be the same equation. Okay. So HCl, strong acid. What's the reacting species? H+. OH-. What's the calcium hydroxide. What's the reacting species? OH-. So now all I got to do is figure out how they go together. So when I take an H+ and I add an OH-, what do I get? I get H2O. There you go. There is your net ionic equation. Do you see that it doesn't even really matter what strong acid or strong base I give you? Your net ionic equation for the reaction is always H+ plus OH- goes to H2O. See, because this is always your reacting species for your strong acid and always for your strong base here. All right, so that's pretty simple. All right, well, what else could I throw at you? Well, I could throw a strong acid and a weak base at you. Okay, so a strong acid, let's do another one here besides HCl. How about HNO3? Okay, that's nitric acid. Okay, weak base. We could do acetate, we could do fluoride, we could do ammonia. Let's do ammonia because that's what we talked about here. Okay, so reacting species for a strong acid is what? What's H+? Goes right there. Okay, reacting species for a weak base is the molecule itself. So that's why we wrote down NH3 here. Okay, now all we have to do is figure out how they go together. So if I tack on H+ to an NH3, what do I get? Well, I get an NH4, so get an extra hydrogen. It was neutral, I added a plus to it. So if it's neutral and I added a plus to it, what's the charge now? +1. And so therefore the formula is NH4+, which is your ammonium cation, which again is one of your polyatomic ions you're supposed to know. See, you gotta know the polyatomic ions. Well, I had you to memorize them because You're going to use them. But there you go. There's your net equation. All right. Okay, well, what else could I throw at you? Well, I guess I could throw a weak acid and a strong base at you. Okay. Weak acid. Acetic acid would work here. Hydrofluoric acid would work here. Let's talk about hydrofluoric acid. Okay. Potassium hydroxide would be a strong base. It's a group 1 hydroxide, so we'll throw that one out there. So HF, what's the reacting species? Well, HF, because it's a weak acid, and the reacting species is the molecule itself. Okay, potassium hydroxide, that's a strong base. What's the reacting species? OH minus, because the reacting species for a strong base is OH minus. So I'm going to write that down. So now I got to figure out how they go together. Well, here's this H plus that's attached to this fluorine over here. Do you think it's attached very tightly? Well, no, it's a weak acid. Sometimes it just comes off, right? Here's an OH minus. So here's what's going to happen. This OH minus is going to pull that H plus off of that HF. If I add an H plus to OH minus, what do I get? Well, I get H2O neutral. I get water. All right. What's left over here if I take away an H plus from HF? Well, I'm left with an F. If I took away a plus charge from something neutral, what charge is it now? It's minus. And there's my fluoride. And there is your equation, your net ionic equation. All right. Notice if you're having problems with the charge thing, your total charges have to balance on both sides. I got something neutral -1 here, total -1, neutral -1 over here. My total charge over here is -1 as well. See, +1 in neutral, +1 over here. One thing at +1 over here, +1 over here. So that's a good way to check yourself, make sure you got your charges right. But that's pretty much it. But look, see, we could have done acetic acid, and we could have done sodium hydroxide. Well, acetic acid, molecule itself, CH3COH, and then OH minus for your strong base. Pull the H off, you end up with water over here, add it to the OH minus, and you end up with CH3COO minus. You end up with your acetate polyatomic ion. It's a different reaction, but the pattern is exactly the same. And so if you know the pattern, you can do anything I throw at you. You don't have to memorize all that stuff. Because there's no way you're going to be able to memorize 3,000 or 4,000 different possible reactions I can throw at you. But the fact that there's only 3 patterns, see, you pretty much got me there. There's nothing I can throw at you that you wouldn't be able to see before. Now, technically, there's a 4th one, and that would be weak acid and weak base. Yeah, it exists, but you don't have to memorize that. Why do you not have to memorize that? Well, a couple of reasons why. Number one, there really kind of is no pattern. I mean, you know, the reacting species for a weak acid is the molecule itself. The reacting species for a weak base is the molecule itself as well. And so, not much of a pattern there. Just kind of work that out, I guess, as it goes. But number two, generally speaking, in the laboratory, you don't run into that. Why do you not run into that? Well, because usually where you run into acid-base reactions is in something called a titration, which you'll do this semester. And basically you have an acid down here in the bottom of the flask, and you have like a base up here in your burette, and then you drip the base down into the acid until you reach what's called the equivalence point, where you have equal amounts of acid and base in the flask down here. If you know the concentration of the base up here, and you know how many milliliters you added, you know how many milliliters of stuff you have down here, you can actually figure out the concentration of the acid in the flask. And so it's a way to figure out the unknown concentration of an acid. Okay, and it works the other way around. If I have a base down here in the flask, I'm going to titrate that with an acid of known concentration. All right? Well, let's say, for example, I've got a base down here and I'm titrating with an acid. What am I going to use for my titration? Am I going to use a strong acid or am I going to use a weak acid? Well, I'm probably going to use a strong acid. Why would I want to do that? Well, because I know for every 1 mole of HCl, I get how many moles of H+. I get exactly 1, okay, because it breaks apart 100%. If I have a weak acid where 1 mole of it gives me 5% H+ or something like that, because weak acids partially break up, Well, now I'm making the math harder. Could I do it? I could probably do it, but why? Why make your life any harder than it has to be? So whatever you want to put up here in the burette, you always have a choice over what you can use, what you do in the burette. You can always put whatever you want in there. You typically don't have any choice over what's in the flask. If what's in the flask is a weak base, well, that's just too bad. Wishing it were a strong base does not make it so. It just kind of is. But you always have a choice over what you put in the burette. And what you put in the burette, you really always want to use either a strong acid or a strong base, because that makes the math nice and easy. So therefore, practically speaking, in the lab, you don't run into weak acid, weak base reactions, or vice versa. It's always going to either be a strong acid, strong base, a weak acid, strong base, or a strong acid, weak base. It's going to fall into one of those three categories. So if you know the patterns for those three categories, you can write the net ionic equation for it. If you know your strong acids and your strong bases, which means you'll know your weak acids and weak bases. So you got to know those as well. All right? Okay. Well, that's acids and bases. So I guess we'll quit there again. Yeah, this is going to be a long chapter in it. So we'll talk about the last class of reactions there, which are redox reactions. And we'll see how much further we get once we get done with that. But yeah, we're making progress. We'll get there eventually. So I guess we'll see you next time. Bye.